So my name is Thomas Edison. I'd like to welcome you to another Series 2 video presented by IPC Irwin and CPD Science. And we're now going to look at another component, the filament lamp, and try and see how its resistance changes when we apply a different voltage across it and record the current. And we'll be looking at whether it's known as an ohmic or a non-ohmic conductor in connection with Ohm's law. So the filament lamp, the first practical version was invented by Thomas Edison, although lots of inventors were involved in its development. They're no longer really used domestically or because they're quite inefficient. A lot of the energy is turned into heat, and the light-emitting diode has replaced this in most lamps. But for the purposes of studying ohmic and non-ohmic components, it's still very useful. So we'll use this circuit initially. We've got an IPC Irwin low voltage power supply there. It's got a rotary selector switch there from 2 to 12 volts. So they're just approximate potential differences. There's a cutout. It'll provide at the most 5 amps. And it's also got an AC supply. So we're using the DC supply. We're connecting it across the filament lamp. And in parallel is an IPC Irwin 20 volt DC 4 meter. Potential difference will be the independent variable here. In series with the lamp, and going back to the power supply, is an IPC Irwin DC 10 amp ammeter, which will be recording the dependent variable. So to carry out the experiment, in this initial setup, all we need to do is change the potential difference, recording a much more accurate reading here, and go up from 2 to 12. Now that will only give you 6 pairs of readings. So what I'd like to do is show you how we can use a rheostat to provide a much smoother change in the readings. So we're connecting this in series. We're coming into the top on the slider and out there. We'll set the output at 12 volts. And if we now move this down to the lowest setting there, we get a maximum potential difference of 12.7 and the current is 1.8. But if we put the whole thing back in circuit again, we still can't get the current down to 0. That's because we're using this in series as a rheostat. So what I'll do is change the circuit round, and we'll go back to the potential divider circuit that we used in one of the Series 1 videos. So our third and preferred way of changing the potential difference across the lamp is to use the variable resistance in what we call potential divider mode, which we looked at in the previous series videos on electrical circuits. So this is the circuit diagram, and you can see that all 3 connections of the variable resistor are used. We connect the 2 ends of the wire resistance coil across the power pack, and we take off the slider of the variable resistor through the ammeter, through to the voltmeter, which is still in parallel with the lamp, and then back to the power supply. So if we now adjust the slider, at its far end here, we've got 0 current going through the lamp and 0 volts across it. So we can actually get down to 0, 0 as our first measurement, and as we gradually increase this, we can get the full range of potential difference and corresponding current across the lamp like so. What we can then do is go back to 0, switch off, and change over the direction of the potential difference by switching over the terminals there, because we're going to be plotting this graph in 2 quadrants. We'll have negative values of potential difference across the lamp as well as positive. And if we switch on there, we can repeat that for the negative potential difference across the lamp. And if we plot a graph we can start to think about whether this component is following Ohm's law and is known to be ohmic or not. So plotting a graph of current on the y-axis against potential difference on the x-axis in both quadrants shows that the graph is a curve and the filament light bulb doesn't follow Ohm's law. It's known to be non-ohmic. And we can look at the label on the graph here to start to think about why that is the case. As more current flows through the lamp, the wire gets hotter, and that affects its resistance. The metal atoms in the filament vibrate faster and further, and this results in the travelling electrons hindering the flow, causing more resistance. So if we look at the values of current and voltage, we measure the gradient, we can work out the resistance, and we can see that it is increasing as the potential difference across it increases. And this is in contrast to the other video where we looked at the resistance of a constant wire, which was ohmic. Well, thank you for watching this Series 2 video on the non-ohmic behaviour of a filament lamp. All these products are available from the IPC Irwin site. If you follow this link, the power supply, the filament lamp, rheostat and the two measuring instruments. And if you'd like the detailed teaching notes that go with this experiment, again, we'd refer you to the Institute of Physics Spark website.